Started. Okay. So my name is Niko Matsakis, and I work on Rust, and I'm here to tell you about it. Um, some of you may have heard of Rust, some of you may not. So I thought I would start with a kind of quick elevator pitch for what Rust is all about. And basically, what Rust is about is kind of, can we have our cake and eat it too, right? Like so many projects, that's what we want to do. But in particular, we want the feeling of a really high-level language, like nice features, closures, and so forth. But we also want really strong safety guarantees, in particular for parallel programming. So we want to make sure we eliminate data races. But we want to do all of that without any kind of runtime and with basically C++ level performance. And the reason is we want to be able to write programs like, particularly, I work at Mozilla, so particularly Firefox, but these kind of large system-scale software that needs to really make the most of the machine. We want to do it in the most productive way that we can, right? And I mean productive kind of over the whole scale of development. So it starts with being able to quickly write code that will kind of do what you want and at the performance level that you want. And here we're basically stealing techniques from C++ that they pioneered, which work really well. Right, so we want to be able to write high-level things like this loop here, which this is a function that tests if something is white space or not. So when you call text.cars, you get back an iterator, which will yield up a sequence of characters. And then when you call .all, so that iterator is lazy. Nothing actually happens until you call all, in this case, which will iterate over them, applying this closure. That's what the parallel bars are, one by one, and testing if those characters are white space. But when this kind of looks nice, it looks like high-level code. But when it compiles down, you just get a little loop with a pointer, just like you have in C, kind of bumping along. Right? This particular example is kind of cute because it turned out that there was a Ruby function doing the same functionality that turned out to be a major performance stumbling block for Ruby on Rails installations because it used a regular expression internally, and it was a very general mechanism. And so some people rewrote it in C, and it was quite long. And then they rewrote it in Rust using the same, plugging it in the same way as a little standard library thing. And they got the same performance, and we were happy, right? They just wrote that in particular. So that's cool. We'd also like to be able to go further and build up higher level abstractions than that. Things like parallel iterators, right? As you probably know from other languages like Scala and so forth, which will do the same basic thing, but it executes in parallel this time. And all the libraries in the world are great, or are useless, I should say, if you can't easily access them. So we also have things like a package manager and stuff that, if you're used to doing C and C++ programming, you know that's not quite so easy, right? You have to go download these things and configure them and integrate them, and it's very difficult. And languages like Java, languages like Ruby have really pushed the boundaries there, and we're trying to also capitalize on that. But all of that is the productivity. That's the first part of productivity, when you first write the code. But what comes later is the long haul, where you have to keep the code working and extend it, and do that without introducing lots of weird bugs. And so imagine that you had that parallel loop that I showed you, which, by the way, iterated over a series of paths and loaded images. And that's working great, but then some other developer comes along and wants to extend it to like count how many JPEGs there are in the file system. And maybe they throw this lines of code in there because they don't know that this is executing in parallel, or they just don't know the implications of that. So what's happening here is we're adding 1 to this JPEGs variable. We're doing it in multiple threads at once. It's going to be an unsynchronized addition, so you're going to get a data race. And the final result will probably not be the correct number of JPEGs, right? So in Rust, if you do this, this code just won't compile. And I'm going to go through some of how that happens later on. You'll wind up with a compilation error that will guide you to the right thing. And this is a really great feeling when you're doing systems programming, I have to say, or any kind of programming. Having a kind of non-subtle bug, or subtle bug, that would have taken you quite some time to find, just raised up quite early, really boosts how much you can get done. Right? And we want to do this not just for kind of data parallelism like this with a loop, but also all kinds of different parallel abstractions. So in Rust, you can use channels, you can use mutexes, and for all of them, we build them up in the library, and we guarantee data race freedom in a kind of equal way. So Rust is out now for about 2 years since our 1.0 release, And we've started to see some use in industry and so forth. So Mozilla was the primary sponsor, and we started to use it. That actually was not a given. We had to kind of prove our way into Firefox. But we've also seen Dropbox integrating it into their server infrastructure, and now on the desktop, NPM uses it in their servers. And you can go to our webpage and scroll through. There's a big list of companies. So it's starting to really get out there and get used. And in this talk, I'm going to go through 3 parts. Usually in my talks on Rust, I focus a lot on memory safety. I'm still going to talk some about memory safety, but I want to try and get through that and talk about some of the other parts of Rust that are really cool and that we don't talk about that much. And in particular, I wanted to talk about traits, which is our technique for doing generic programming. It's very similar to Haskell type classes, and how we model closures and how those two interact. So let's start with the memory safety, though, because that really provides kind of a foundation that everything else builds on. So the first thing to understand is, what exactly is the problem anyway? Now, if you've worked a lot in languages with garbage collectors and so on, you may not be that familiar with kind of all the myriad ways that you can shoot yourself in the foot when you're writing code in C++, right? So I think a lot of people think of like returning a pointer to the stack after the function returns, and that is one way you can go bad. But there are also somewhat more subtle ways. Like here I have a vector of strings, and I'm going to access, and this is going to make a reference, this line of code, to the first string in this vector, and we'll call it element. And then I'm going to add something new to the string. Oh, what's happening here? Okay. And the problem is, if it happens that this vector, I think I'm standing on the chords, that's the problem. If it happens that the vector is at capacity, then we might reallocate the backing buffer, copy the old data, put the new string in the new location, and update the vector's data pointer. And everything looks fine from the point of view of the vector, but we still have this element reference just dangling around, right? And if we were to go on and use it, that would be very bad indeed. So this is a kind of bigger problem called iterator invalidation. Basically, while you're walking through or have references into a data structure, you really shouldn't be changing it. And it has 2 key ingredients in it that show up time and again in all these different kinds of problems. I think the first one is that we have aliasing. We have more than one path to reach the same memory. And the second one is we have mutation. And either one of those on their own is pretty much okay. Because if you just have mutation, the memory is only reachable from one path. It's kind of clear what to do to account for the new changes you made. But if you have aliasing in the mix, then you don't always able to track for that, right? So the vector updated its data pointer, but it can't find this element that's in another stack frame it doesn't even know about. So what we do in Rust is we bring to bear some of the techniques that have come through research, the research community in the last few years, or last couple of decades, I guess I would say. And I'm going to kind of explain them here at a more intuitive level. We call it ownership and borrowing. So basically, there are 3 ways to work with data in Rust, 3 primary ways. And what we'll see is that in every case, we either have aliasing or we have mutation, but we never have both. So the first one is ownership. That's kind of the central building block. And the idea here is that every value that you create has an owner, which is a variable. So in this first line, this is some Rust code. In that first line there, I'm making a vector, and I'm storing it into the variable vec. And vec is then the owner of this vector. I can mutate this vector. So you see I said, I should point out, let mute vec. In Rust, we tend to make mutability is perfectly okay, but it tends to be something that you opt into, that you write so that you see it when you read the code. And in this case, we're declaring when we make the variable vec that the data it owns is going to be mutable. So here we can mutate the vec, we can append things to it. And then we're going to call take. And this is where it gets interesting, because the take function has an argument whose type is vec of int. And what that means in Rust is I'm going to take ownership of some vec of int. When you call me, you give me my own vector that I own. So we'll copy the data over into the take stack frame. And now this take is the owner, and we are not. So our variable is basically, it has no value left in it anymore. And take can execute. And when take reaches the end, it takes all the data that it owns and it throws it away. That's what functions do when they return. So that's when memory gets freed. And this is basically how memory management works in Rust. You make values, you store them in places, you move them from place to place, and when their owner goes away, goes out of scope, the memory gets freed, much like a C++ destructor, if you're familiar with that. So you might wonder, okay, now this memory's been freed, what would happen if this function tried to use the vector afterwards? And the answer is that you can't, because the compiler remembers what you had and what you've given away, and it won't let you access things that you've given away. Right? So this would be an error if we tried to use vec afterwards. And this is pretty handy, of course, for, like in this case, preventing us from accessing freed memory. It's also a really neat building block for building APIs, because you can have sort of logical tokens that give you permission to do certain things, and when they get consumed, you lose that permission. Right? So that's ownership, and that's the most common pattern in a sense, but it's also a pretty inflexible one. A lot of times we don't want to give ownership of a function, we just want to write a function that will read some data real fast and compute a result for us. And for that, we have shared references. So the idea of a reference is kind of analogous to borrowing in the real world. Right? If I give you a book, I don't mean for you necessarily, sometimes I do, but to own it. I just want you to read it and give it back to me when you're finished. And it kind of works that way. So if we have this vector, which vec is the owner of, and we call this use function, if it takes a reference to an int, that's basically going to be borrowing the vector from the owner. So it's not taking ownership, it's just using the data. And on the other side, we don't pass the vec, that would be giving ownership. We write ampersand vec, so we're creating a reference and passing that. In terms of runtime, that's going to be a pointer. And that means that the use function can now read as much as it likes. And when it's done, it will just, it doesn't own the data, so nothing gets freed. We just pop the reference and come back. At this point, since we only lent the data out, we now still have access, and we can go on and use vec some more afterwards. So the trick is, I call them shared references because you can copy them. So if you have one shared reference, you can make many copies of it, and they all refer to the same data. That is the aliasing part. That implies then that we shouldn't allow mutation, and indeed we don't. Right? So if you have a shared reference, I can't, for example, push onto the vector. That API is not permitted, nor can I increment the data that's in the vector. I can only read from it. Any one of those attempts will result in an error. And I should say that this is, I'm simplifying here. There are times when you do want to allow sharing and mutation, but we force you, in that case, you go through there has to be some kind of API that protects it. So a common example will be like, I want to share a single mutex across multiple threads. Now, if I have a mutex and I couldn't share it, it would be kind of pointless, because only one thread could ever use it anyway. But that's exactly an API that guarantees some protection. So that's shared references. And the last thing then is mutable references, which is kind of the same idea. You're lending out data, but this time you're lending out not an immutable version of it, but data that can get changed. So here's a function which takes two vectors, from and to. The from is a shared reference that we already saw, but to is a mutable reference, and it's going to copy data from one to the other. Right? And so since this is a mutable reference, we're allowed to make changes. We can call push. And it's kind of interesting to look at what happens when we execute this function. First off, when we come down to this for statement, we're iterating through a shared reference to a vector, and in Rust that means that we get back shared references to its contents. And so we started out borrowing something, we're now borrowing the things in it. So basically the type of element is going to be a reference to an integer. And that's why when we call to.push, we do star elem to dereference that and pull the data out. And it's going to go append it onto whatever vector 2 refers to, somewhere up the stack, or down the stack, I guess. And when we come to the next iteration, we're going to do the same thing we would do in C++. We have our reference to the sum pointer. We're just going to bump it along at a constant offset from where it was. Okay? And that's a really efficient way to iterate, of course. It's also really good if the thing in your vector is not just an integer, but some bigger structure. But now, you might ask, what would happen if we took that same execution, but we allowed from and to be the same vector? This would be exactly another instance of iterator invalidation, right? Because now from and to are both pointing to the same place, and maybe when we push onto the vector, we have to reallocate the backing buffer, free the old one, and we're left now, as we go to the next iteration, we're left again with this dangling pointer that we had before. Of course, that can't happen because we don't allow you to create shared references and mutable references to the same thing at the same time, right? And in general, that's kind of the rule in Rust. So if you tried to do it, if you made a shared reference and a mutable reference, you would get an error depending on which one came first. And more generally, we maintain this rule that if you have a mutable reference to something, there is no other way to access that memory. You can't go through the original path, nor can you have shared references at the same time. All right. So that's, in a nutshell, the three patterns that we're going to see. And I wanted to go through them both because this is the most unusual part of Rust, but also because these patterns kind of crop up in different places throughout the language, where you're going to have to deal with either you're working with memory that you own, or memory that can be read but not written to, or memory that you're going to be mutating. So let's look a bit at traits. So traits are our mechanism for doing generic programming. And we saw earlier on this iterator trait. And I'm going to kind of go through that one in detail. So this is an example of using iterator. It is a dot product. It iterates through two vectors, vec1 and vec2, of integers. And it works by, you kind of start out going through one vector, and then zip with another one, which means that you'll walk pairs of the two things. And just like zip in many other languages, if they're unequal lengths, this will take the shortest of the two. And then we call map. Now, I want to emphasize, iterators in Rust are lazy. So at this point, nothing has really happened. We're just setting up the computation that we're going to do. Right? And when we call map, we're saying after we zip these pairs together, the next thing we will do when we do the computation is we'll multiply the two parts. And so we'll get back an integer that has the product, or a series of integers with the product. And then I can call sum. Right? This code, it looks quite high level. When you compile it, what you wind up doing is generating custom code to do just exactly that one computation. And the compiler then sees that, and it even actually ends up being vectorized, which is pretty cool. And we can then go up, if we were to apply this parallel iterator, we would have the same basic idea, except we just change .iter to .pariter, and now what we wind up with is we're going to break those two vectors up into sequences, distribute them over the cores, and each core, when it processes a sort of chunk sequentially, will do the same thing that we saw before, so you'll have SIMD layered on top. So that's pretty neat. How does it work? This is how you define a trait, and this is, in fact, a portion of the iterator trait. So a trait is kind of like an interface, and there's an implicit parameter, which we call the self parameter, which is the type for which the interface is implemented, right, or the trait. So in this case, that's the only parameter we have. We also do support kind of multi-parameter traits, and we'll see one later, where you have more than one implementing type. And inside of a trait, there can be many things. And in this case, the first one we see is an associated type, which is basically what kind of element are we iterating over. And you can reference it this way. So here you're saying, given this self, which is some kind of iterator, what is the item for that? And finally, you see that there are methods that you can invoke. And one thing that's kind of interesting about them is that they don't have to have a self parameter, but they usually do. They have a self parameter, and they take it in one of three different ways. This one is an and mute self method, which means it's going to mutate the iterator. The idea is the iterator will update itself, preparing to produce the next value for you. But you can also have and self methods and by value self, as we'll see later, and those kind of take ownership or take shared references. Right? And if you only have, say, a shared reference, then you can't invoke the mutable methods. You can only use the ones that are suitable for the kind of access you have. So we get to use traits in a pretty kind of OO feeling style. So if iter is some variable of some type that implements iterator, then we can write iter.next, and that will invoke the iterator method. But internally, that's basically desugared to this functional form, and you can use this one too if you prefer, where you extract out the method as a function, and then you pass it the receiver as the first argument, and it dispatches, in that case, to the right implementation. And you see that when you use the dot form, you kind of don't have to put the and mutes and some of this other computation that we do in the desugaring. So the result of this would then be option of t::item, where that's the associated type again. All right, so that's how the iterator trait looks. This is the this is the zip struct, how one would actually implement the zip iterator, which is a kind of nice example because it's non-trivial but not too complicated. So basically, when you call .zip, you're going to get back an iterator, as I said, that is basically represents the suspended iteration, saying when I execute, I will zip. This is what that struct is. So it's a generic struct. It has two type parameters, A and B, and they're both required to also be iterators. So zip is going to combine their results. And it just, inside its fields, there's really no state in particular, just the two iterators that are being combined. So this is what it looks like here. On top we have the struct we saw, and down below we have something called the impl. This is basically where I say I'm implementing a trait for a particular type, where you supply what the methods actually do. Right? And this is the generic implementation. So the implementation applies to any A and B. It will implement iterator for zip of that A and B. Right? So you don't have to be as generic as your type. You could implement iterator for zip of some particular kind of iterator if you wanted, and so on. This is the most generic form. So zip will work over any two iterators. And the kind of values it's going to produce is a pair of the two items that we extract out from A and B. And you can see that also, of course, gets mirrored in the return type. So inside the actual definition, you see that Rust has some of this functional feeling, so that you would get from, like, if you were using OCaml or some other language. So basically what we do is we just call the next method on self.a and call the next method on self.b, put them inside of a pair, and then match on the pair. And if we get two sums, we can pull the A and B out and put them into another pair, and so on. Right? And if we don't get, then we'll return none. And none in this case is basically signaling, hey, we're done with the iteration now. So that's what zip looks like. And you may wonder then, okay, we saw what the struct zip, capital Zip, but how do I use this method form? How did that get enabled? The way that that works, at least in the case of iterator, is that in addition to having this base set of items that we saw before, the top two, you can add additional items down below, and these ones have defaults. So zip is defined on the iterator trait, and it's basically defined for all iterators by default. So some particular iterator might choose to override it, but if they don't, they'll get this default implementation, which says how to zip myself with some other iterator of type I. And here I'm using this where clause notation. It's exactly equivalent to the notation we saw before. Just sometimes it's nice to pull them out. And all it's going to do is create an instance of the struct, packaging up self and other together. So the last thing I want to emphasize is the compilation model. I said that this was a generic impl that works for any kinds of iterator types. And the way that that works at compilation time is we use the C++ sort of monomorphization strategy. So basically, we're going to make a specialized copy of this impl specific to the sorts of iterators that you happen to be using in your program. And that's how we get that full optimization. And we do that to, as far down as we have to go. Now, sometimes you don't want that. And we do allow you to use traits as types, which gives you more like an object that you can invoke with dynamic dispatch. This is less common in practice. Okay. So that was the trait system kind of in a nutshell. And the next thing I wanted to talk about is how closures work and how they integrate with the trait system. Because basically, whenever you're defining these sort of combinatoric APIs, right, we saw zip, you often end up wanting little bits of code that you can stick in there to do customizable operations like the closure here in map. But closures in Rust are not built into the language. The only sense that they're built in is that we have syntactic sugar for them. But really, they're just types that implement traits. And so when you see a closure expression like that one, that's kind of syntactic sugar for some sort of struct, like this one, that captures whatever that closure needs from the environment to execute. So any of the variables that it uses. In this case, the closure didn't use any variables from the environment. So it's an empty struct, which means that at runtime it has 0 size and doesn't actually even exist. Right? It's just a type that we trace through. And then here in the map, you would just make an instance of that struct. And this struct implements a closure trait, which is like when you call something, that's sort of an overloadable operator that goes through a trait. But in fact, we don't have just one. This is where the ownership patterns come in again. We actually have 3 traits, depending on how you're going to call it. So for example, the base layer is a function that only gets called once, fn once, and it defines an output associated type. That's the return type of the function. So this is a multi-parameter type class, I should say. So the self, the implicit self, is the environment that's being invoked, and the A is the kinds of arguments that this thing accepts. So a given thing can implement, can sort of be overloaded with different sorts of arguments. But in any case, the fn once, the key point is it takes ownership of the closure itself when it gets called. So that implies you can only call it at most once, because you can only give ownership once. The other traits go through the other modes. And so fn mute has a mutable reference, which means you can call it as many times as you want, but only once at a time, because each time you have to give a unique reference over to it, and you can't have more than one unique reference at the same time, of course. And this notation here is called a supertrait notation, and basically we're saying if you implement fn mute, you must also be implementing fn once, because if you can be called multiple times, surely you can be called just once, right? That's sort of a subset. And similarly down here, we have the fn trait, which has shared references, which corresponds to something that's being called in parallel with itself, or maybe recursively, or something else, just basically more than once at a time, right? And so if you put these traits down, you see that as you go down the hierarchy, you get more ways to call the function. It starts at the most restrictive, and then it gets more flexible. And you kind of pick the level for what you need as a consumer of a closure. But on the other hand, as you go up, the closure gets more power. Because if it's only going to be called at most once, that means it has ownership of its environment. It can move things away. Right? And if it's going to be called sequentially with a unique reference, then it can make mutation to the variables in its environment, and so forth. So between these two, the closure kind of decides how much power it needs, and the caller decides how much power it can give it, and they better match. So when we have the map combinator, that's also a struct, just like zip. It has a base iterator I, and it has a closure f. And because map is in a sequential iterator, that's going to be fn mute, because every time you do the iteration, it will invoke this closure to do a map on the next item. Right? Now you see here there's a little bit of sugar. This bound doesn't quite look like other bounds. It has parentheses and not angle brackets and so on. Well, I guess this is actually just sugar. So we found the bottom tedious to write, so we made a shorthand for it, basically, that applies to closures. So what happens is the argument types get tupled up. So there's always one argument A, which is always a tuple of the different arguments to the closure. And the arrow R is just specifying what the return type is. Right? So this syntax says, here's the arguments. And this is saying, I implement fn mute with the associated type of R. So that's sequential iterators. And I showed you this example of parallel iterators that would prevent a data race. They look pretty similar. The main difference, if you have parallel map, the main difference is this. Instead of fn mute, you take fn, because now you're going to be using a shared reference, which is split across different threads. And so if we look back to our example of the data race, it's kind of interesting to look at how this particular closure would be desugared. So the previous closure we saw in the dot product had no state. It wasn't very interesting. This one is more interesting because it uses a variable from its environment, this variable JPEGs, and it's going to be incrementing it by 1. So when we desugar this, it's going to look something like this. It's a struct that has a field, which is a mutable reference to the JPEGs variable. And the compiler does this automatically on our behalf. It looks at how you use each of the things that you take from your environment and picks what mode you should be using. So because we're mutating this, we need a mutable reference to it. And then the actual implementation of fn mute that the compiler will synthesize looks kind of like this. And you can see it's actually the same as the code we had before, except that instead of saying JPEGs plus equals 1, I'm now rewriting that systematically with get this reference out of my self pointer and dereference it. And in order to actually do this mutation, the most I can implement is fn mute, right? I can't implement fn, for example, because if I have a shared reference to a mutable reference, that's still aliasing, right? I have many copies of a unique reference. It's still a shared reference, and we won't allow mutation through that path. So in terms of our two parts, we have then that the closure is actually providing just these two impls, right? Something that can be called fn mute or can be called fn once. And on the other side, the parallel iterator wants something that provides all three, and this is exactly where the errors arise. So the lesson here is that, or what I'm trying to show you is basically that when you're using these different mutable references and shared references and building up your APIs, you can express the invariants that the clients of the code need to follow, and then get, so that you will get errors and so forth at the right times if there would be a data race. So that's the summary of my talk. So I hope I've kind of got you some of your interest in the way Rust works and also how generic programming in Rust works and how you can build up APIs. If you're interested in learning a little bit more about Rust, there's a lot of resources online, or you can, of course, talk to me later. But I wanted to point you to a few. So naturally, our website has everything on it. And we spend a lot of time on IRC. But we also have a new edition of our Rust book that's come out with a kind of fresh approach focused on ownership first and so forth. And I think it's really good for learning about Rust. And I also have a bunch of screencasts that cover some of the ownership model, which is what's at intorust.com. So thanks, everybody.
So we have some time for questions. If you just want to use the center located mic.
Hi, thanks for the talk. Like the thing that you showed us was those selecting the right type of the closure is pretty neat. But I wonder, so for example, if it's the way to say that this closure is like pure or something like that, or it uses only the resources that are specifically given to this closure. But what about, like, for example, console printing? Like, if I try to print in console in parallel, would there be problems?
So the console API is a global variable in Rust, and as such, it's actually required to have a kind of thread-safe API. So what basically happens is when you call, like, say, print, we acquire a lock for the duration of the print. So what you're getting is not really a pure function, it's a shared function. So it's kind of everything that you can do anything in that function that is permitted through a shared reference, right? Which usually means it's immutable. But as I said, there are exceptions for things like mutexes and so on. And so consoles and other kinds of I/O events, they either they operate through. In the case of console, it's global, so it's kind of a special case, and we have this lock. But for most things like streams or channels and so on, then you have two endpoints, and we use the affine systems. Or you have to have a mutable reference to send a message, or you have to have ownership to send a message, things like that. Or you can do that anyway if you want to restrict it.
Okay, thanks.
Hi, I think Rust is just an amazing achievement because it's the first time or just about the first time we've seen one of these kind of linear or affine type systems actually make its way into practical use. So it's just incredible. Well done.
Thank you.
I'm wild with envy. I want to steal all the best ideas I can and put them in Haskell. But how do you know that what you've implemented is right? Right. So I've got personal experience having screwed up many times, right? So you build a system, you think it's right, but then there's some nasty corner case that shows you, GHC can segfault, and that's very embarrassing. How are you confident that the Rust implementation, never mind bugs in the realization, just the system is correct?
Okay, so, well, you just added the first caveat I was going to say, which is I know that it's not right, because I know of several bugs in the implementation, but some of which I would say were maybe perhaps bugs in the thinking that went into the implementation, but we'll pass that aside. But what we're doing in that, we don't know, of course. We don't have formal safety proofs. But what we are doing in that direction is collaborating with a lot of people. So Derek Dreyer and Ralph Young, as a PhD student, is doing the most direct work here in this Rust Belt project, where they're basically modeling a logic in Iris that is very similar to Rust, and which they are proving the soundness of many different Rust abstractions and so forth. And now what remains to be done, though, is to go from Rust surface syntax down to their logic, which is different. But that's one effort. And there is a really big open problem there, though, kind of an open space, which we're also attacking, which is I didn't talk about it much in this talk, but we have the very foundations of the system are not implemented in C. They're implemented also in Rust, but in a kind of superset of Rust, the unsafe Rust, which basically lets you have pointers. It's kind of Rust plus C pointers. And that defining how precisely, what exactly is allowed in that subset, what kind of optimizations we can do, what the memory model is, and so forth, is a pretty challenging problem, and we're still working on that. And I think that's an area where Rust is actively evolving. But in practice, that's kind of not something you interact with every day unless you're building low-level libraries and so forth. But it is definitely part of this effort. And before we can answer that question, we have to kind of define those semantics more precisely, which is why we're trying to do it.
Good. Maybe there'll be some feedback from that process that might in turn influence the design.
Yes. Oh, definitely. Cool. We've already kind of had some episodes of that.
Great. Really good.
Yeah.
Thank you.
Hi. I was curious, so you mentioned that you can use traits as parameters, and you said something about you get object-like semantics. And so I don't really know anything about how Rust packages work, but what happens if I write a package that takes a trait as like an argument, and now I have like some binary blob? Do I get like a link time like what happens when I link against a library that's using a trait as a type?
That's a good question. So the answer is that when you have a type like this, you'll notice that I wrote ampersand iterator. The ampersand is important because we make sure that if you're using it as a type, the value that is behind that object could be of any size, right? So we make sure you use indirection, first of all. And secondly, what we're basically giving you is actually a sort of a fat pointer. It's a combination of a pointer to the data and a vtable, which has all the implementations of the different methods. And you can only do this for traits where we can realize a vtable. So there are some features that don't work that way. And in that case, what will happen is the downstream client will synthesize a vtable and give it to the upstream library.
Does that get like, is it possible that that will get optimized away?
Yeah, that can get optimized away. LLVM does devirtualization under certain circumstances. And in fact, we used to rely exclusively on that. So in ye olde Rust of yore, we didn't have the traits, the closure system I showed you here, and we relied exclusively on devirtualization. And it worked pretty well as long as you don't have too many like layers of indirection and so on. But
cool. You know. Great work. Thanks.
Okay, let's give the speaker a round of applause.
Large system scale software that needs to really make the most of the machine. We want to do it in the most productive way that we can, right? And I mean productive kind of over the whole scale of development. So it starts with being able to quickly write code that will kind of do what you want and at the performance level that you want. And here we're basically stealing techniques from C++ that they pioneered, which work really well. Right? So we want to be able to write high-level things like this loop here, which this is a function that tests if something is white space or not. So when you call text.cars, you get back an iterator, which will yield up a sequence of characters. And then when you call .all, so that iterator is lazy. Nothing actually happens until you call all, in this case, which will iterate over them, applying this closure. That's what the parallel bars are, one by one, and testing if those characters are white space. But when this kind of looks nice, it looks like high-level code. But when it compiles down, you just get a little loop with a pointer, just like you have in C, kind of bumping. Started. So, okay. So my name is Niko Matsakis, and I work on Rust, and I'm here to tell you about it. Some of you may have heard of Rust, some of you may not. So I thought I would start with a kind of quick elevator pitch for what Rust is all about. And basically, what Rust is about is kind of can we have our cake and eat it too, right? Like so many projects, that's what we want to do. But in particular, we want the feeling of a really high-level language, like nice features, closures, and so forth. But we also want really strong safety guarantees, in particular for parallel programming. So we want to make sure we eliminate data races. But we want to do all of that without any kind of runtime and with basically C++ level performance. And the reason is we want to be able to write programs like, particularly, I work at Mozilla, so particularly Firefox, but these kind of later on. You'll wind up with a compilation error that will guide you to the right thing. And this is a really great feeling when you're doing systems programming, I have to say, or any kind of programming. Having a kind of non-subtle bug, or subtle bug, that would have taken you quite some time to find, just raised up quite early, really boosts how much you can get done. Right? And we want to do this not just for kind of data parallelism like this with a loop, but also all kinds of different parallel abstractions. So in Rust, you can use channels, you can use mutexes, and for all of them, we built them up in the library, and we guarantee data race freedom in a kind of equal way. So Rust is out now for about 2 years since our 1.0 release, and we've started to see some use in industry and so forth. So Mozilla was the primary sponsor, and we started to use it. That actually was not a given. We had to kind of prove our way into Firefox. But we've also seen Dropbox integrating it into their server infrastructure, and now on the desktop, NPM uses it in their servers. And you can go to our webpage and scroll through. There's a big list of companies along. Right? This particular example is kind of cute because it turned out that there was a Ruby function doing the same functionality that turned out to be a major performance stumbling block for Ruby on Rails installations because it used a regular expression internally, and it was a very general mechanism. And so some people rewrote it in C, and it was quite long. And then they rewrote it in Rust using the same, plugging it in the same way as a little standard library thing. And they got the same performance, and we were happy, right? They just wrote that in particular. So that's cool. We'd also like to be able to go further and build up higher level abstractions than that. Things like parallel iterators, right? As you probably know from other languages like Scala and so forth, which will do the same basic thing, but it executes in parallel this time. And all the libraries in the world are great, or are useless, I should say, if you can't easily access them. So we also have things like a package manager and stuff that, if you're used to doing C and C++ programming, you know that's not quite so easy, right? You have to go download these things and configure them and integrate them, and it's very difficult. And languages like Java, languages like Ruby have really pushed the boundaries there, and we're trying to also capitalize on that. But all of that is the productivity, that's the first part of productivity, when you first write the code. But what comes later is the long haul, where you have to keep the code working and extend it, and do that without introducing lots of weird bugs. And so imagine that you had that parallel loop that I showed you, which, by the way, iterated over a series of paths and loaded images, and that's working great, but then some other developer comes along and wants to extend it to like count how many JPEGs there are in the file system. And maybe they throw these lines of code in there because they don't know that this is executing in parallel, or they just don't know the implications of that. So what's happening here is we're adding 1 to this JPEGs variable. We're doing it in multiple threads at once. It's going to be an unsynchronized addition, so you're going to get a data race. And the final result will probably not be the correct number of JPEGs, right? So in Rust, if you do this, this code just won't compile. And I'm going to go through some of how that happens.